All right, so now that we're done with chapter 3, we can move on to chapter 4, in which we're looking at, as you can see, applications of derivatives. And these are many different techniques that we can use to find different interesting results using derivatives. It's quite a long list, by the way, if you look at it. We're going to cover a lot of material here, but we'll see it used throughout the rest of the course, as well as in Calc 2. But here the focus is more on the applications than on deriving rules, although there will be rules. Most of them were covered in chapter 3. So now we can focus on what can we do with these derivatives now that we know how to calculate them. So we'll start at the beginning with the so-called linear approximations. And remember, all this is based on the logic that a derivative is itself simply the slope of a tangent line. And so we're going to put that idea to good use here. What this will enable us to do is use tangents to come up with approximate values of a function when they can't be estimated directly. Okay, so now we start with this key equation, which shows us that the equation of a tangent line can actually be written in this very interesting way. And so this will be more clear, I hope, with the diagram in the next slide. So I've repeated that equation here. So here's what's going on here. You notice how this y equals f of x is a curve. Directly above is a straight line. This is, of course, the tangent line to the function. It touches exactly at the point x equals a. And directly to the right of that, we have a very close point, a plus dx. Dx, as you'll see later on in this chapter, is called a differential. Think of it as an infinitesimally small change in x, or you could imagine this as delta x, as delta x keeps getting closer and closer to 0. At some point, we reach some limiting case, and we now call that dx. Okay, so it's like this. This is as small as delta x can get without actually being 0. Now, if you notice, of course, we also on the vertical axis have the corresponding y values, f of a and f of a plus dx. So the slope of this equation, as you can see down here, or this tangent line, I should say, is f of a plus dx minus f of a over a plus dx minus a. So we're going to put this or use it at least one different application. So we're going to start with a specific example to see how this works. And that example is f of x equals 1 over x. So based on the power rule, after writing 1 over x as x to the minus 1 power, you can see that the derivative of 1 over x becomes negative 1 over x squared. Okay, here's why, because there's an implicit 1 here, 1 times x to the minus 1. 1 is our k, n is negative 1. So based on the function, the derivative rather of nk x to the n minus 1, we'll have minus 1 times 1 plus x to the minus 1 minus 1, or minus x to the minus 2, which in turn can be written as negative 1 over x squared. All right, fine. So we're going to need that in a minute. Here's the graph. And, well, I've already gone in and sketched in the final result. But the graph itself, you can see, is something we've seen before. This graph is 1 over x. You can see it only occurs in the first and third quadrants. And you'll notice that the domain of this function is all values except 0, because that vertical axis is an asymptote. So what we're aiming for is we're trying to ask ourselves, at the point x equals 2, what would be the equation of this tangent line? Not just the slope, but the equation. And so that's what this formula is for. Okay, so I showed it to you a minute ago. This linear approximation is the equation of a tangent line, written in a slightly unusual way. So what we're going to do here is use this information to come up with the exact equation. So what do we need? Well, We know that f of x is 1 over x. A is 2. We're interested in discovering the equation of the tangent line when x equals 2, so that a becomes 2. F of a is 1 over 2 because you're just plugging the 2 in here for x. The derivative f prime of x we've already seen is negative 1 over x squared, which implies that f prime of a, or 2, would therefore be negative 1/4. So if you plug those results in here, make this a little bigger. Yeah, so what you've got is f of a, which we know is a half. And then we have plus f prime of a, which is negative 1/4 right here, times x minus a. All right, so in other words, by plugging in the values we just got, this is what we come up with. And now we can simplify algebraically. And we have a half minus 1/4 x plus a half. Ultimately, we end up with y equals 1 minus 1/4 x. And that tells us, of course, two things. We have the intercept and the slope. The slope of f of x when x equals 2 is negative 1/4. And that in turn tells us, by the way, that's what this graph is meant to represent. F of this point hold on. It should be f prime of 2. That is the slope of this function at that point, but it's also the first derivative. In other words, what this tells me is that the derivative of f of x equals 1 over x is negative 1/4 when x equals 2. So in other words, we wanted to know the derivative itself, but only at that point. And so this is what we've got, negative 1/4. If we wanted to know the derivative at a different point, we'd of course have a different result, because as you move along that horizontal axis, the curve itself, the slope of that curve is changing. Okay, so what we would like to be able to do, though, under some conditions, it may be good enough. In other words, what we may want to be able to do is come up with an approximate slope for this curve at a given point. So here's what I mean. Let's say that we're really interested not in x equals 2, but x equals 2.1. Now, because we know the function itself, we can find this information by just plugging in 2.1 into the original function. Okay, which I've done down here. But you can see here, by using this equation, by replacing the x with 2.1, you can see what we've done is we've come up with the approximate slope of the tangent line to the curve when x equals 2.1. It's only slightly different. And that might be close enough. Okay, now, now you might want to know, why would you ever want to do this? Well, here's an example from finance. What you're seeing here is a curve that represents the relationship between the price of a bond and a specific rate of interest called the yield to maturity. And what this curve tells me is that with high prices, the yield is low, and with low prices, the yield is high. In other words, they're going in opposite directions. Now here, what we've done is we've noted that the current price of this bond is 1,000 and its yield is 5%. What if I wanted to come up with an approximate value for what would happen to this bond's price if the yield rises to 6%? Well, that's what this is for, this thing. This is going to give me, the equation of this line, this tangent line at that point. Let me write it as y equals plus f prime of x minus a. Now we can change the notation a little bit here. Oh, whoops, wait, this is it. Here we're assuming that the price depends on the yield. So we can change the notation slightly. No, actually, it's okay. We'll leave it like this. We don't need to change it. We get the idea. But what we're trying to do here is use this equation of this tangent line to come up with the approximate value of the bond when the yield rises to 6%. Now, the reason why we have to do this is because with the bond pricing relationship, we don't have a nice formula that represents the entire curve. What we can do is evaluate the price for every one of those yields, but we don't have an explicit equation that gives us the entire curve. So otherwise, none of this would be necessary because you would just plug the 6% right into the formula and come up with the correct price. But unfortunately, it's not that simple. So for a case like that, you may want to use this approach where you're taking the tangent line and using it to at least approximate the values of the function when x is at least close to 5%. The key there is close. If the x is way out here somewhere, for example, the approximation would be very, very poor. It's only if we stay very close to here that this method works. Okay, so now what we're going to do is introduce a little bit of new terminology, I guess. This function that we've been looking at is sometimes called the linearization of f of x near a. So in other words, it takes some curve or other and creates a straight line out of it. So yes, we can call it the tangent line, but to be more general, we can call it the linearization at the point x equals a. Now, if you note, at any other point, it would be a different linearization. It's only when x equals a that this is the actual tangent line. So let's do a numerical example here. Imagine we're using the function x squared, square root of x. You can see up there, what it is, it starts at the origin, and then as x increases, the curve increases at a progressively decreasing rate. In other words, it's flattening out. So we want to know what the function's value is at x equals 9, but we can do that directly from the formula. But we also would like to do the same thing for x equals, or a rather, equals 9.1. So in other words, I want to approximate square root of 9.1 using this linearization method. Now, of course, this isn't absolutely necessary because we have a function. I'm going to do that right now. I'm going to plug in 9.1 into the calculator and find its square root. That's approximately 3.0166. Let's see how good this method really works. 3.0166. That's not, of course, the whole answer. There's a lot of decimals here, but let's just say that's what it's actually giving us. Now, that's what we get by plugging in directly into the function. But if we don't have that ability, like with the price yield curve, then we have to try something like this, the linearization method, where we calculate the tangent line and then use that to come up with our approximations. So here's the formula. And then again, it's just the tangent line, L of x equals f of a plus f prime of a, x minus a. So we start by looking at a equals 9. And by the way, here I've shown with the power rule how to take the derivative of radical x. And just keep in mind that the square root of x is the same thing as x to the 1/2 power. There's an implicit 1 here for the coefficient. So we have k x to the n. K is 1, and n is 1/2. So when we take the derivative, we get n k x to the n minus 1. And of course is 1/2, k is 1. Then we have x to the n minus 1, which is 1/2 minus 1, or negative 1/2. So ultimately, we have 1/2 times 1 over radical x, or 1 over 2 radical x. And then f prime of 9 is 1 over 2 radical 9. So that's f prime of 9. We're going to need that up here. So what that means is that this curve at x equals 9, this tangent line has a slope of 1/6. And it kind of looks like that. It's very flat, and it's clearly got a positive slope. So plugging everything into this linearization function, what this tells us is that the equation is 3 plus, remember the derivative is 1/6 when x equals 3. And this is what we end up with. That's the tangent line. Okay, that's what you're looking at right there. So how does that help us? Because now I can come up with the estimate of the slope of this function at any other value of x, as long as it's close to the original function, a value of 9. Anything far away, like if I try to do it with, let's say, 50, I'm going to get a terrible answer. But 9.1 we'll try, and we'll see that it's very close. So here's what we have. Here's our linearization function. Which technically is only true when x equals 3. Actually, let me try to draw that again. So when y equals 9.1, actually, I'm sorry, I got these two backwards. 9 and 3. That's better, because this is radical x. So what about at 9.1? Let's say that that's right here. So it's kind of hard to see. It's so small. Let me try to draw it on the next slide. Okay, that's not too bad. So let's say, I'm going to exaggerate it a little bit, but let's say it's way over here at 9.1. So you can see there's a gap here. This is the actual value of f of 9.1. And this one on the top is the approximate f of 9.1. So because of the way the curve is shaped, that means our approximation will be slightly too high compared to the actual value of 9.1. So when you plug in these numbers, okay, so remember this formula equals, here it is. So here's f of 9. In other words, the square root of 9 plus the slope, x minus a. So what we're going to do differently here is that we're going to replace the 9 with 9.1. So L of 9.1, the intercept hasn't changed, 1.6. This is the only part that changes. And you can see that this is 3.01667. So this is the approximation. Actual f of 9.1, you can get from our calculator, the square root of 9.1 is about 3.01662. You can see, as we predicted, this is using the tangent line. And this is the actual value. The tangent line is a little bit higher because, as you can see, the actual function increases at a decreasing rate. So the line is directly above it. So using this approach, we have a slightly overestimated function. It's slightly too high, but it's not that far off. I mean, really, it's not that far at all. The reason why it's so accurate is because we didn't move too far away from x equals a. Okay, like I said before, if we tried to move from 9 to, let's say, 20, you would find that the approximation is actually not very good at all. All right, and then here's the book's graph of this. It's obviously better than what I was doing. You can see the two curves aren't that far apart as long as we're reasonably close to 9. After that, they start to deviate from each other quite a bit. So again, you'll use this in applications where you have information of some kind, but maybe not the exact function that you need. Like with the price yield curve, you have the ability to price individual bonds, but you don't have an actual function that you can use to directly solve for them. So anyway, now differentials. We started to briefly discuss this. You might recall that there's different ways of expressing a derivative. If we start out with f of x, the so-called first derivative can be written in 3 equivalent ways at least. There's others too, but we're not going to bother with them. We have f prime of x, we have dy dx, and we have y prime. And the reason why we keep running into multiple notations that mean the same thing is because math wasn't invented by one individual any more than English was. So you notice how in English we have a lot of words that actually mean the same thing. That's because they came from different languages. You're probably aware that England was conquered many, many times in its history by the Romans and the Angles and the Saxons and the Danes and the Vikings and you name it. And so each time, apparently, the English language absorbed the invaders' language. So that before you knew it, English was a huge, essentially almost a buffet of languages. And so there's many different words that mean the same thing. And so something just like that happened here. You may not know, but the two individuals who were held to be responsible for calculus, I'll just mention this briefly. And, it's never going to be possible to be 100% sure, but calculus is attributed to two individuals. One you've heard of, Isaac Newton. I'm sure you've heard of him because he was so he did so much work in so many different fields, mostly related to physics. And in Germany at the same time, a mathematician named Gottfried Leibniz was also working on a lot of the same concepts, which we now know as calculus. So they're jointly, wait a minute, did I spell that right? No. Okay, there we go. So they're both considered to be I guess you could call them the fathers of calculus, but you'll notice when we go through calculus, in a lot of cases, the notation that we're using was either invented by one or the other. They both had different notations. They didn't even know that the other one was working on this, by the way, because Newton was in England, Leibniz was in Germany, and they didn't know each other. They never even heard of each other. And lo and behold, it turns out that they're both working on practically the same thing at the same time. So, and Newton was the type of person, he would write up all these brilliant papers and then he wouldn't publish them for years and years and years. I guess he was worried that he wanted to make sure that they were perfect before he published them. So he was very secretive, let's just say. So anyway, so we got Leibniz and Newton both working on the calculus. And so we typically use the notation which seems the most straightforward. So the notation that we're using here is given to us by Leibniz, dy dx. Okay, that was his idea to call it dy dx. And so when you see that notation, you can think of Gottfried Leibniz because he's the one who created this. And so the idea here is that the d means that here you've got a small change in x, delta x. And this is what we're going to call an infinitesimal change in x. In other words, it's the smallest change we can have without it actually being zero. And a lot of results in calculus are based on limits. As some variable gets very, very, very small, we want to know what's happening to some other variable. Because this way we can avoid having, go directly to zero and winding up with division by zero. Instead, what we're trying to do is say, well, what happens as we get really close to this point? So the d's are called differentials. And so the first derivative is simply the ratio of two of these differentials. So anyway, what we're going to do here is rewrite this linearization slightly. And instead of what we started out with, we're going to replace the x with a plus dx. Okay, so in other words, we're thinking in terms of a and something very close to it, a plus dx, rather than x itself. Anyway, so when we go through all of this, what ends up happening is that after a bunch of algebra, we end up with this. So in other words, the first derivative at a given point A can be thought of as the linearization of a plus dx minus f of a. So now here's a graph that shows this. So we've got red is the linearization, as we've already seen something just like this. Blue is the curve. Now you can see we started at A on the x-axis, and then we increased ever so slightly to a plus dx. So in other words, the gap between these two is dx. On the vertical axis, with these 2 points, in both cases, the x-coordinate is a plus dx. The difference, though, if you notice, this one on the top is the actual value of the function at that point. This is the approximate, the linearization of it. Or in other words, think of it as the point on that tangent curve, a tangent line. So let's see how this can help us. So we've got y equals x squared plus 2x. It's a parabola. Find dy and evaluate when x equals 3 and dx equals 0.1. I just want to improve on that graph a little bit. Okay, what is this all about? Well, okay. The function that we're interested in is x squared plus 2x. And of course, based on the power rule, f prime of x would therefore be 2x plus 2. And remember, the initial starting point was 3. Okay, so then, since f prime of x equals 2x plus 2, dy dx equals 2x plus 2, dy equals 2x plus 2 dx. So oh boy, no, I better do that again. So what we're going to do is we'd like to find out the approximate value of this function when x is not 3, but 3.1. But using this approach, not plugging it into the formula. Okay, so in other words, we're actually going to be here somewhere. So we can find out the actual value right here by plugging 3.1 into this expression. So remember, the original function was x squared plus 2x. That implies that f of 3.1 is 3.1 squared plus 2 times 3.1. And that's going to give us 15.81 exactly. But what's the approximation that we're going to come up with? All right, let's find out. So remember, dy, based on the results we just had, so x is 3, but the change is 3.1 because we're looking for 3.1. This is what we're after. So that means that dy equals, as you can see here, we're replacing the 2 with a 3. This is our delta x. This is 0.8. In other words, when dx is 0.1, dy is 0.8. Or you can think of this as +15 plus 0.8. Okay, so in other words, using this approach gave us 15.8. That would be right here. The actual value is 15.81. Not bad. Okay. So in other words, again, this is all about trying to find the approximate value of a function at a given point when we don't know the equation of the entire function. Instead, we have to rely on finding individual values. So we use the tangent approach to come up with approximate values that we need. Now, here's one. If you're going to, of all the ones we're going to see here, this one may be the most important one. We're often going to be interested in finding out if a function has a maximum or a minimum value. And so, by the way, a little bit of a Latin lesson here. Maxima is the correct plural of maximum, and minima is the plural of minimum. Also, the words minimum and maximum collectively are known as extrema. Okay, and so extremum is the singular of extrema. So in other words, if a problem says to you, find the extrema for this function, what they mean is find out if there are any maximum or minimum points. There may not be any, there don't have to be. But if they do exist, we'd like to know what they are. So, sometimes it's easy to do this. Sometimes it's not so easy. For example, let's say I have something like this, just a straight line. Well, the function doesn't ever actually have a maximum or minimum. It goes from negative infinity to positive infinity. And there's the range is all the real numbers. So there's no extrema. Well, there you go. Now, how about this case where we have let's say a parabola? You might recall that a parabola is the graph of a quadratic equation. And if a is positive, then the parabola faces up. If a is negative, then it faces down. But what I wanted you to see here is that there's some point where the parabola gets as small as it can get. This is our minimum point. In other words, the range cannot go below this point. The y can never have a value below this point. And here we have what we call a maximum. So the range is restricted to that point and everything down below it. So with these two cases, there in this first case, there is no maximum because the function keeps going up to infinity. And over here, there is no minimum because the function just keeps going down to negative infinity. Okay. Now, here's an interesting one. Sometimes a cubic function, for example, can look something like this. Now, what's happening here is that here it reaches a point where it doesn't want to go up any further, but then it starts to fall, but then it reaches some minimum point down here, and then it starts to rise again. So this point, even though it isn't the largest value of y in the entire function, for a pretty wide range of values of x, this is the largest value of y. And the same thing is true down here for this point. So sometimes you hear this referred to as a local maximum. Or sometimes it's called a relative maximum. It may not be the largest point in the entire function, but it is within this area. Sometimes in math, we call this a neighborhood. Within this neighborhood, this is the largest value of the function. So this one, the same exact reasoning, is called a local minimum or a relative minimum. Because it may not be, in fact, I didn't draw it. I mean, if you kept drawing this down, you can see it will eventually fall below this point. And the same thing here. So it's only a maximum or minimum within a certain range of x values. But that's also important information. And now, what about these parabolas, by the way? Let's take a look at them one more time. This is as small as the function can get. So this is not a local or relative minimum. We're going to call this a global or absolute minimum. In other words, this is it. This is as small as it can get. The function cannot go any lower than that. Y is going to be at that point or greater. So this tells us that this is the largest, period. No matter, there's no other part of the function where we can find a larger or smaller minimum, I should say. And then what about the other case, the parabola that faces down? Well, I'm sure you can guess what this is called. This is called a global or absolute maximum. Okay, so now what you may have noticed about these points is they have something in common. Let's take a look at this graph. We have three extrema. There's two local maxima and there's one local minimum. What they all have in common is that the tangent line at that point is flat. It has a slope of 0. Okay, so that's how you can identify these points algebraically. You can take the derivative of the function, and at any point, any x, where the function has a slope of 0, that guarantees that this is either a maximum or a minimum of some kind. So in other words, when we start testing for these points, this is the starting point, basically. Now, this by itself, the tangent line being 0, cannot tell us whether this is a maximum or minimum. That requires more information, but at least it can identify all the extrema that are in the function. So you can see why this is called an application of derivatives, because it'll enable us to find these points. Now, you can easily imagine why this could be so very, very important. Because let's say, for example, these concepts can be used in economics to find the minimum cost of producing a product or the maximum revenues that result from producing the product. So you can easily imagine you had a function that represents our profits or our costs or revenues, whatever. We could use this setup to figure out where should we produce our product in order to either minimize our costs or maximize our revenues. All right. So again, we'll go back and revisit this concept of local extrema. There can be several local extrema, although there don't have to be any. And so here's an example where there's one of each, a local maximum, a local minimum. And again, you can see that they both have a flat, the tangent line is flat, horizontal. Which means that f prime of x is 0 here, and f prime of x is 0 here. Now, here's the formal definition of a local maximum. A local maximum, f of x is a local maximum at x equals c if there exists some interval a to b containing a point c such that f of c is greater than f of every other value in that interval. Okay, so in other words, whatever our interval is, there's some point in there such that the function evaluated at that point is at least as great as every other point in that interval. But I mean, I think intuitively it's easier to just think about it as the point where we have a tangent line with a slope of 0. But that's what it actually means. And then, of course, you can figure out what the local minimum is. There's still a some point in that interval where the function is as small as it can get within that interval. And as we've already discussed, any function can have multiple local minima or local maxima. Although there can only be one absolute maximum and one absolute minimum, we can have as many local minima and maxima as we want. Now, some more definitions. The so-called critical point. Now, the critical point can actually refer to a couple of things. The critical point of a function is that interior point that we just talked about, that c, which is inside some interval, where the derivative is 0 at that point, meaning that the tangent line is flat there. But if the derivative is undefined at that point, we still refer to that as a critical point. So what this means then is that wherever we find extrema, the points in which we find the extrema are themselves called critical points. Okay. Now, the critical point itself doesn't have to refer to a maximum or a minimum, but a point which is a maximum or a minimum must be located at a critical point. Okay, because remember, the critical point includes bizarre cases where f of c, a prime of c rather, is undefined, where there's discontinuities. All right, now, Fermat's theorem. Now, Fermat was a real heavyweight in mathematical history. A lot of these mathematicians who develop the material that we're learning have very interesting life stories. And Fermat I don't remember his exact years. I think we're looking at the 17th century here, but let me confirm this. 17th, early 17th century, I see. Okay, anyway, so he was a brilliant, brilliant mathematician. And so there was a problem that he was working on. He was trying to prove, and I don't remember exactly which one it was, but he apparently, before he died, he wrote a note in one of his books and he said, I've come up with an elegant proof for this theorem. And then he didn't tell anyone what it was. Okay, or he never wrote it down, or it got lost, whatever happened. So it suddenly became an obsession with mathematicians to prove what was called Fermat's theorem. Let me see if I can look it up. It was there's no natural numbers, meaning the 1, 2, 3, etc., such that x to the n plus y to the n equals z to the n if n is greater than 2. Well, I don't know how important that really is, but apparently mathematicians worked on this for centuries. I think recently somebody did come up with the result. Somebody proved it. Yeah, there it is, 1994. Now remember, Fermat was living in the 17th century, and it took until 1994 to prove that theorem. Now, we don't know if he ever found the proof himself or not. All that we know is that he thought he did. But it was like this, the white whale of the math world for all those centuries. We've got to find this proof. We've got to prove Fermat's last theorem. And so finally it happened. But it took a long time. And so there's others too. There's others that are still waiting proofs. But anyway, so Fermat's theorem is not that theorem. This is a different theorem where he says that f of x is a local extremum and it is differentiable, which means it rules out the case where there's a discontinuity. Then f prime of c must be 0. Okay. So exactly like here, those 2 points are guaranteed to have a slope. The tangent lines have a slope of 0. But we can have cases where there is a flat curve where yet it is not differentiable at that point. Okay, so here in the upper left-hand corner, we have certainly there is a critical point here where we have the derivative is defined. But now here's one where we run into trouble with derivatives. It's a little hard to see that. Let me zoom in on it. The problem, whoops. Oh, I'm sorry. I know I'm hitting the wrong button. The point with the derivative, you've got to have the curve has to be smooth and continuous. And the word smooth is the key one right here. The second function here, it is not smooth. You see, there's a sharp break from the left to the right. So in other words, the slope, the idea behind a derivative is that the slope of the function, no matter whether you're coming from the left or the right, is converging to some specific value. Here, that's not happening. As x approaches from the left, we have a very different slope than as x approaches from the right. So where they meet, we do not have a derivative. The derivative can only be defined if the slopes on either side of that point are converging to each other. Same thing here with this big V. At that exact point, there's not going to be a derivative. It's simply undefined. And then, what happened there? And by the way, if you notice here, there's a brief moment here at C where there is a tangent line which is flat, and yet it's not an extreme point. And over here, well, over here the slope is undefined, the vertical line. So that is not considered to be an extremum. So in other words, and by the way, the top of this little peak here, it is still considered to be a local maximum. It simply does not have a derivative at that point. Okay, f prime of c is undefined. On the right, f prime of c is undefined, but they're still considered to be extrema. Now, luckily, most of the time, we're not going to run into these bizarre cases. Okay, so what we're going to try to do is focus our attention on finding these extreme points. So in other words, we're going to look for all the critical values that the function has. And then what we need to do is figure out whether it's a local maximum, local minimum, or in some bizarre cases, neither. All right, so here's an example of this. We've got this cubic function, which, usually means it goes through a bunch of twists, ups and downs. And, well, I've already done this for you, but this is the SimiLab graph. You can see the 2 points where the function has a tangent, which is flat, are those 2 points. Now, how do we do this? Well, what you're doing is you're taking the derivative of this function. And there's how would you do this algebraically if you didn't have a graph in front of you? You take the function, you set the derivative equal to 0. Now, because the derivative here is a quadratic equation, there must be 2 values of x where we have a critical value, or critical point, rather. So we're going to use factoring here, although we could just as easily use the quadratic formula. And you can see that we have x minus 4, x minus 1 equals 0. That implies that x minus 4 equals 0, and or this equals 0. So in other words, we end up with 4 and 1. These are the critical points. The question is, are they maximums or maxima, minima, or neither? All right, so here I plug them into the formula so you can see what the y values are. Okay, so that's where these 2 points came from. X is 1 and x is 4. Those are the corresponding y values. So we have to determine whether they are local maxima, local minima, or neither. How do we do that? Well, what we just did is sometimes called the first derivative test. But I think I mentioned before, all this can do is help us identify the extreme points. Or I should say the critical points. What about determining whether these are maxima or minima or neither? Well, we've got a few options, but we can try the so-called second derivative test, which I think we're going to save that for later. For now, it's enough to note that if you look at these points, what you'll notice about them is that, yeah, not only is the slope is flat, but in the first case, the slope is going from positive to 0 to negative. In the second case, the slope is going from negative to 0 to positive. Uh-oh. Yeah, every once in a while, my tablet kind of craps out. I'm going to fix it right now. There we go. And so in other words, what you can do, once you recognize that f prime of 1 is 0, you can solve for f prime of any points below 1 or above 1, slightly above or below, and see what their signs are. Okay, so like here, if you solve for f prime of 0 and f prime of 2, let's say, you would have discovered that f prime of, oh, actually, in this case, it's got to be more than 0. Whatever it is, as long as you're close to 1, the derivative changes from negative to positive, positive to negative here, and down here from negative to positive. And that's how you would know that these are relative extrema. In other words, a relative maximum and a relative minimum. Now, well, anyway, so for now, that's enough. Later on, we'll bring this back, this discussion, and look at the second derivative test. Now, what about global extrema? Well, let's see. We know already the difference between the two. Here these functions have a global maximum and a global minimum. This function only has a relative maximum and minimum. It does not have an absolute maximum or minimum, because that would be infinity. That would imply that there's some value that the function never goes above or below. So a local extremum is restricted to a certain interval. A global extremum applies to the entire domain. All right. So, yeah, I think we've already seen some of these. These are actual functions that have a critical point, which is not, well, actually, in the first case, it's neither a maximum nor a minimum. There's a special name for that we'll see later on. Okay. In the second case, we do have an absolute maximum, although they don't show you how they came up with that result. But we do know that the tangent is flat there. And based on the function itself, the range is actually restricted to 1 down to negative infinity. So this has to be an absolute max. And then finally here on the right, you've got a bunch of relative maxima and a bunch of relative minima, because this is the cosine of x, and it goes through a repeated series of waves. And so there's actually an infinite number of relative maxima and minima. And then, got a few more oddball cases here. We've got actual discontinuities. We got all kinds of weird behavior. So we may or may not have an absolute maximum or minimum. This first one has an absolute maximum, but no minimum. Second one actually does have one of each. And then the third one has an absolute minimum, but no maximum. Okay. All right. So there's not that much left here, is there? Wow, we're zooming along this one. So this is a very theoretical chapter, by the way. We're just introducing. This is only 4A. No wonder it's so short. But then there's also 4B and 4C, I believe. So, but again, remember a lot of this is very theoretical, but it's going to give us a lot of background for what we need to do throughout the rest of the course and in Calc 2. So, all right, so I guess we'll stop here and we'll pick it up. What we're going to do is wrap up this section 4A or chapter 4A with our discussion about how to identify global extrema. Okay, and then in 4B, let me just open that up real fast. Let's see what's going on there. Yeah, there's a C and a D. Wow. Yeah, some more theorems which help us understand more of the properties of derivatives. But when we get into C, I believe, well, we'll see how it goes. But at least one or two of these topics are very applicable to real world situations. A lot of these results are theorems that are going on in the background with when we're looking for maximum and minimum, but we should be familiar with them. So anyway, like I said, we'll stop here. We'll pick it up next time. See you later.